In this segment, I want to show how we evaluate expressions in our expra language. Now, in fact, there's more than one way we can go about getting the result of an expression. We can do an evaluation, and that's what I'm covering in this segment, but also we can think of doing it rather indirectly, that we can compile the expression to a sequence of instructions for a virtual machine, and then we can execute that sequence. And in fact, we would expect to get the same answer with compilation or direct evaluation. So now in this segment, we'll look at evaluation, and then in the next, we'll look at compilation and execution. So what about evaluating an expression? What type should that function have? Well, it takes an expression, which is this structure that represents, it's a tree that represents an expression. And what we want to do is get from that an integer. So the expression might be something like 2 plus 3 times 4, which is this, it's the tree that we've seen built with an add and a mult and so on. And what we want to do is throw away all that structure, well, or resolve all that structure to just give us a number. Well, the first case is straightforward. To evaluate a num expression, we just return the number it contains. What about evaluating an add? Remember what an add is. It says it's an add, so we know it's an addition, and then it has 2 sub-expressions. And what we need to do is work out the value of the first, which will be a number, and the value of the second, which will be another number, and add those 2 together as numbers to give us a number. So the evaluation of the expression add turns into an add addition over numbers. And similarly, for multiplication, we evaluate the 2 sub-expressions and multiply the results together. And you can see that animated here with this expression 2 plus 3 times 4. Each of the numbers that appears in that expression just evaluates to itself. And then we can evaluate the sub-expression 3 times 4 to give us the number 12, and then the sub-expression 2 plus to give us 14. So that shows the evaluation working in practice. But there's a problem. What if we have an expression that contains a variable? What value can you give to that variable? Well, what we do is we say we will evaluate the expression in the context of what we call an environment. And an environment is something that carries values of variables. And so now we pass that environment around as part of the evaluation. So the first argument now to eval is an environment. Evaluating the number n in the environment is just n. And evaluating an add and a mul, you evaluate the 2 subtrees in the environment and then add together those 2 numeric results to give a number. The new case here is what you do with a variable. And the answer is that what you do is you look up the value that v has in the environment. So what I've described here is a high-level approach to how the environment works, but we better think about what the environment will be. How do we represent it? What's the type, capital E, env? And how do we define the lookup function? Well, here we are. What I'm proposing is we define the type env, and I've got a type synonym here, that it's a list of pairs of characters and integers. And here's an example. env1, character A is paired with 12 and B is paired with minus 11. So you can see that as saying in this environment, A has the value 12 and B has a minus 11. And then we can look up a value in the value of a character in that environment and get an integer. We need to decide what to do in the case that a character isn't in the environment, isn't given a value. What I've done here is say the value is 0. But equally well, we could say it's an error, or but I've just said arbitrarily I've chosen it to be 0. But otherwise, if there are pairs in the list, how do we define the lookup function? Well, the first thing in the list will be a pair, and so we pattern match that against x, pair xn. So the first thing in the list says x has the value n. So if the variable we're looking for, v, equals x, then we've found our answer. It's n. Otherwise, if v isn't x, we have to look in p's, in the remainder of the list. So that's a classic list recursion. We define lookup v on something cons p's in terms of lookup v on p's. And that's given us the complete story about evaluating an expression with variables. We have the environment, and then we have, as we saw on the previous slide, we can define the evaluation function for every possible kind of expression.